Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hello students, as you remember in our previous class we studied about integrated rate law. Basically, if you remember the differential rate law, we can integrate that rate law, and after integrating the rate law we obtain the integrated rate law. The integrated rate law, it will be different for different order of reactions because those things we have seen. For example, if you remember, this is for the first zeroth order reaction. This is the differential rate law, and once you integrate these things, this TR and DT, and you get this is the integrated rate equation. So final equation we get as this. So concentration of R is equal to minus KT plus R naught, and then we show this kind of plot that we can draw. And then this is the similar thing we have seen for the first order reaction, and later on we saw certain graphs and some numerical problems as well. And finally, what we obtained, this equation is very important for the first order reaction. K, which is a rate constant, is equal to 2.303 divided by T log R naught. R naught is the initial concentration of the reactant divided by R, where R is the final concentration of the reactant, or R concentration at time T. Now we are going to study about the half-life of a reaction. So half-life is what, as you understand from the name itself, half-life of a reaction. So half-life for a human being, half-life means if my age is suppose 80 years, so 40 years is a half-life, one can say. So for a reaction, half-life it means that the time required to decrease the initial concentration of the reactant by half. Means if the half of the reactant is already consumed, the total time required is called the half-life of the reaction. So the half-life of a reaction is a time in which concentration of a reactant is reduced to one half of its initial concentration, and it is represented by half-life of reaction is represented by T half. So this T half, if you see somewhere in the question or anywhere, it means it is talking about the half-life of the reaction, and half-life of the reaction means half of the, by reaching this time, half of the reactant is already consumed. For a zero order reaction, what we know, this is for the rate constant K is equal to R naught minus R divided by T, where R naught is the initial concentration, R is the concentration at time T. So R naught minus R is the concentration which is consumed, concentration of reaction, the reaction that reactant that is already consumed divided by T. This is what the equation that we have seen in our last class. So this is the equation, R naught minus R divided by T. So what do you see here, that if this concentration, this is the concentration at time t, the remaining concentration of the reactant, if this one becomes half of the R naught, means half of the reactant is already consumed, and that time, the time required to reach this concentration is represented as T half. So this T we can represent as T half, and this R is equal to R naught by 2. So R naught is the initial concentration minus R naught by 2. What we obtain, this R naught 2 R naught, this is R naught, so this will become 2 R naught minus R naught divided by 2. So the R naught divided by 2 into T half. So K will be equal to R naught divided by 2 into T half. So T half will be equal to R naught divided by 2K, and this is how this expression we obtain for the half life of a zero order reaction. And what we see here is that T half is directly proportional to the initial concentration for the zero order reaction. So T half for a zero order reaction is directly proportional to the initial concentration of the reactant, as well as what we see, the T half is also dependent on the rate constant K. So the T half is inversely proportional to the K that we saw here in this equation. So for a first order reaction now, the first order reaction, that this is the integrated rate law that we obtained. K is equal to 2.303 divided by T log R naught by R. If this R naught becomes, this R becomes R naught by 2, then T, this T is T half, that time we represent as T half. So the 2.303 divided by T half means T half is what? The time required, a time in which the reactant concentration becomes half of its initial value. Half of its initial value, so that time is T half. And what we know, for the, if suppose there are more than one type of reactants, like 2, 3 reactants are involved there in the reaction, then in such a case this T half depends on the limiting reagent. This is one thing that you have to understand. So anyway, so 2.303 divided by T log R naught by R is the integrated rate law. And now 2.303 divided by T half, so log, then if we are putting checking this time T half, so this R will become R naught by 2. So log R naught divided by R naught by 2. So T half, now what we obtain, 2.303 T half log 2. This will become log 2 because R naught and R naught will be cancelled out. So this will become log 2. So 2.303 divided by T half into log 2, so is equal to K. So T half is equal to 2.303 divided by K log 2. We have just interchanged the position of T half and K, and that one can do very easily. Was T half, it will go here, it will be in the multiplication, and since K is in multiplication, it will go in the denominator here. So T half is equal to 2.303 by K log 2, and it means 2.303 log value of log 2 base 10 is 0.301. So on multiplying 2.303 into 0.301, which is log 2 by K, we get this value as 0.693. So T half is equal to 0.693 divided by K for the first order reaction. So this value is a constant. What we know, for a particular reaction, first order reaction value of K is also constant. So T half is constant for a particular reaction, and this is what we know for the half life for the radioactive disintegrations usually we study about. So for a first order reaction, half life period is constant. And why it is constant? Because 0.693 is already constant, and this expression you can see this K is also constant, and this K is the rate constant, which is constant for a particular type of reaction, a particular reaction. And that K value of K, and so this 0.693 by K will also be constant under given condition. However, what we know, one thing you have to remember, this value of K also depends on certain factors. For example, it depends on the temperature. So if you increase the temperature T half or decrease the temperature, if you vary the temperature, T half may vary. However, under the similar condition, T half is a constant, and T half is constant because it depends on this. It can be obtained as 0.693 divided by K. So for the first order reaction, half life period is constant, and that is, it is independent of initial concentration of the reacting species, because we see in this expression the concentration terms are not there, which means it is not dependent on the concentration or initial concentration of the reactant. So what we obtained overall is, for a zero order reaction, T half is proportional to R naught and T half is proportional to R naught, this expression that we have seen here. So T half is R naught divided by 2K. So T half is proportional to R naught. However, for a first order reaction, T half is independent of R naught. Let's now take this question. A first order reaction is found to have a rate constant K into K is equal to 5.5 into 10 to the power minus 14 per second. Find the half life of the reaction. So what we know, half life of reaction, you can apply this equation directly. So half life of a first order reaction is T half is equal to 0.693 divided by K. Value of K is already given, which is 5.5 into 10 to the power minus 14 second inverse. So 0.693 divided by 5.5 into 10 to the power minus 14 second inverse, and this will be equal to 1.26 into 10 to the power 13 second. Now let's take this question. So that a first order reaction, so that in a first order reaction, time required for completion of 99.9% is 10 times of half life, which is T half of the reaction. Means the completion, reaction is completed by 99.9%. It means 99.9% of the reactant is already consumed. So what is the remaining about the amount of the reactant? The remaining amount of the reactant that one can represent as RT is equal to the initial concentration of reactant minus the reactant which is consumed. And the 99.99% is consumed. It means what? What fraction it is consumed? It means 99.99 divided by 100 is a fraction of the initial concentration already consumed. It means the remaining amount is the R naught minus 0.999 into R naught, which is 0.001 into R naught. This fraction of the reactant is only left to us. After the and this is the, it means this is the remaining concentration. Now what can apply the expression for the first order reaction, and this is K is equal to 2.303 divided by T log R naught divided by RT. The RT here have represented RT as the remaining concentration or concentration at time T, which is left over. So what can we do? In this expression one can put the value. This time is we do not know, we have to obtain. So time required, we have to find out that this time required T is 10 times of the T half. This is what we have to prove. So we don't know what is the value of T. The value of K is also not known to us, but we can obtain value of T in terms of value in terms of K. And this value of K will be constant for the reaction. Now what can we do? The 2.303, let's see that this time, let's consider this time required to for this much completion is 99.99% completion is T. So log R naught divided by after 99.99% completion of the reaction, this much amount is only left. So this amount one can put here 0.001 R naught fraction of the initial concentration. Now from here what can we take? This K into T will be equal to 2.303 log R naught. This R naught will be cancelled out. So this log 10 to the power minus 3. This is 1 divided by 10 to the power minus 3. So overall it will become log 10 to the power 3. So K will be equal to what? K is equal to 2.303 divided by T log 1 upon 0.001. It means 10 to the power minus 10 to the power. This one is 1 divided by 10 to the power minus 3. So it is log 10 to the power 3. Log 10 to the power 3 means the value, this is base 10. So its value will be 3. So one can KT is equal to 2.303 log 10 to the power 3. So T is equal to 2.303 divided by K into log 10 to the power 3, and log 10 to the power 3 we can put as 3. So T is equal to 2.303 divided by K into 3. This is what we have obtained in terms of K, the value of T. Now what we know, T half is equal to 0.693 divided by K. So the value of T half we also know in terms of K. So T half is equal to 2.693 divided by K. Now if you remember this value is nothing but 2.303 into 0.301. This value 2.303 into 0.301 is this 0.693. So this value one can put here. So T divided by T half will be equal to 2.303 into 3 divided by 0.693, and this K will be cancelled out. So 2.303 into 3 divided by this 0.693 is what? 2.303 into 0.301, and this 2.303 0.303 will be cancelled out. So this the value is what? 3 divided by 0.301, which is approximately equal to 10, and this was what we had to prove. So we obtained the same value, means the T, the time required for 99.99% completion of the reactant is 10 times of the T half, and this is 10 times of the T half we have obtained. Now this all the things for the first and second order reactions are summarized here in this table. For the zeroth order reaction, not first and second, zeroth and first order reaction. So zeroth order reaction, one can represent the reaction type as R to P. First order one can also represent it as reaction to product R to P. The differential rate law will be equal to, as we have shown earlier, minus dr divided by dt is equal to K, or similar one can write it as dr divided dr dt is equal to minus k. Means d dt of r is equal to minus k. And this for the first order reaction, because we know that this rate of reaction also depends on the concentration of the reactant to the power 1. So, differential rate law for this case will be written as dr of dt. So, minus 1 can start with minus dr concentration of r dt is equal to k r to the power 1. So, dr dt will be equal to minus k r to the power 1, r to the power 1 is not shown here, power 1. So, dr of dt of r is equal to minus k r. On integrating this equation, we can obtain the integrated rate law, and this integrated law we obtained earlier as R naught is equal to R plus KT, or KT is equal to R naught minus R. So, this is integrated rate law. For the first order reaction, this was for the zeroth order reaction. For the first order reaction, integrated rate law we obtained as R is equal to R naught e to the power minus KT. If you remember this equation, here R is equal to R naught into e to the power minus KT, or the similar thing we can write in the terms of log value of log as well. So, that is also an integrated rate law equation. So, integrated rate law equation can also be written in terms of log. So, KT is equal to ln R naught by R, and this ln one can change into base 10, which is this is the natural base. So, one can convert it into the natural base, and to convert it into the natural base, we know we have to multiply the value with the 2.303. So, what we see other thing is a straight line plot we obtained in the case of zeroth order reaction for the R versus T plot. In the concentration of the reactant versus time plot, concentration of the reactant versus time plot, if you see here, again I will reach a concentration versus time plot. It was a straight line plot here for the zeroth order reaction. However, for the first order reaction, log of R or log of R naught by R versus time plot was a straight line plot. So, the straight line plot we obtained in the case of zeroth order reaction, when the graph was plotted between concentration of reactant and time. However, we obtained the straight line plot in the case of first order reaction when the log of R, where R is the concentration of the reactant, is plotted against the time. So, this is the straight line equation, and the half life we have just seen. Half life of the zeroth order reaction is equal to R naught divided by 2k, where R naught is the initial concentration, and for the first order reaction we see the half life is equal to 0.693 divided by k, and 0.693 is nothing but ln 2, because ln 2 which means log base e2, log base e, if we can change into base 10, we so log base E2 is equal to log 2.303 into log base 10 2, and log base 10 2 is 0.301. So, 2.303 into 0.301 we obtained as 0.693. So, ln 2 by k is nothing but 0.693 by k. The unit of k, we have seen a general expression for the unit of k, and that we have seen earlier, and in the case of zeroth order reaction, the unit of k means the rate constant. It is concentration per unit time, and if the concentration is represented in terms of mole per liter or the molar concentration, so which is mole per liter time inverse or the second inverse. For the first order reaction, rate constant what we saw, it is 0.693 divided by k. So, the k is what? 0.693 divided by t half. So, from this expression itself one can write the rate constant, the unit of rate constant. The 0.693 is a dimensionless quantity, it is a number, and the t half, this time is if the inverse, it is time inverse, and if the time is represented in second, it will be second inverse. So, the unit of k will be second inverse for the zero order reaction or the time inverse. If the time is given in the minute, so it will be equal to minute inverse, or minute to the power minus 1. If the time is given in terms of years, so it will be year inverse, and if it is hour, it will be hour inverse. Now the similar thing one can see the graphs and other things. This for the second order reaction, though I have not explained the second order reaction, the integrated rate law, but the rate expression one can see, and this similar thing we have seen. So for the second order reaction, one can write rate. This is just a summarized table for all the first and second order reaction. So the differential rate law, we can write if the reactant is represented as A. So in the terms of concentration of reactant A, earlier we have represented in the terms of R as the reactant, here it is A. The rate is equal to the differential rate law will be equal to, and this is the average rate, is minus delta concentration of A divided by delta T, which equals to K. For the first order reaction, it will be equal to minus delta A delta T divided by delta T is equal to K into concentration of A to the power 1. For the second order reaction, we see the similar thing, the rate is represented as minus delta A by delta T, and this will be equal to differential rate as the rate law. This is the rate law expression, so this is equal to K into concentration of A to the power 2. One can integrate this expression because this delta A divided by delta T one can write as minus D concentration of a dt, and minus D concentration of a dt one can write, so one can integrate this expression as well. So on integrating this, one can obtain the integrated rate law, and the integrated rate law is this. The differential rate law, it should be actually the terms of d dt. Here it is shown in the delta, so it should ideally be d dt. The integrated rate law, A is equal to A naught minus KT is for the zeroth order reaction. Similar thing we have seen in this table as well. This R naught KT is equal to R naught minus R. Here R is A naught minus A. One can write. So A naught minus A is equal to KT. This is a same thing we see here. The integrated rate law for the first order reaction is this. A is equal to A naught e to the power minus KT. K is, in this case, all the cases K is the rate constant, or ln A is equal to ln A naught minus KT, the same thing one can write. And the integrated rate law for the second order reaction will be, once you integrate this, dA minus dA dt is equal to Ka square. On integrating, you will obtain as 1 divided by A is equal to 1 divided by A naught plus KT. Now one if you plot a graph between A and T, A versus T plot, you will obtain a straight line here. In this case, you may not obtain a straight line. If a plot between concentration and time will not be a straight law expression, it will be exponential. So there will be exponential decay in the concentration with the time. In this case, the decay will also be there, and this decay is faster than the exponential decay, and this decay will be as per this expression. This 1 divided by A is equal to 1 divided by A naught plus KT. So if you just put the value of A at the time T, obtain the remaining value at the different times and plot a graph, you will see this kind of graph will be obtained. So here the slope here will be more than the slope. The magnitude of slope in this case will be more than magnitude of slope in this case. To obtain a straight line graph, what we do here, a straight line graph is directly obtained between concentration versus time plot. The concentration of versus time plot. So if you get the straight line, so we can easily obtain the slope, and with the slope we can obtain some other important quantity as well. Here the slope for the zeroth order reaction is minus K. The rate constant we can obtain as slope, and that value we just multiply with minus 1. So K is what? K is equal to minus slope. So slope, whatever the value of slope we obtain, we multiply that with the minus 1, we will obtain the rate constant. In this, the case of the first order reaction, we obtain the slope, rate constant as the slope as well, minus of the slope as well. However, in that case, we have to obtain a straight line, we have to plot a graph between long concentration, this value ln concentration of A versus time plot, and this value here, the intercept value, it gives ln of A naught, this value. And in the second order reaction, one has to plot a graph between 1 divided by concentration, this versus T, to obtain a straight line graph. And in this what we obtain, this magnitude slope again in this case is the rate constant, but in the slope is directly equal to the rate constant. However, in other cases where the slope is, we obtain negative slopes. For the zeroth order and the first order reaction, we obtain value of k as minus of the slope. In the second order reaction, we see the slope is a positive, we obtain as a positive value, and the positive value, and so the rate constant is exactly equal to the slope. And as we know, the rate constant of a reaction cannot be negative. Rate constant negative means what? Reaction is not happening. So it can slope. If the slope is negative, it means some error is there, and some means we have to do something. And anyway, from the expression one can obtain here itself, we see here slope is equal to minus k. Slope is equal to minus k. So k will be equal to minus slope, and slope here is negative. That we know. The slope is what? Tan value of this tan theta, and theta we obtain here is that we know it's more than 90 degree. So the relative rate versus concentration term, if you look at for the zeroth order reaction, what we see, if you increase the initial concentration, we don't see any change in the rate of the reaction, because we know the rate of the reaction is equal to the k, the rate constant for the zeroth order reaction. And this expression we have also obtained earlier. So just you can see come here, and this value, the rate of the zeroth order reaction is equal to k, and the k is rate constant. It means the rate is constant. So it doesn't depend on the initial concentration. Whatever the concentration you choose, the rate is always going to be k. It is not going to change. So the for the zeroth order reaction, there are many terms that you may be confusing for you. Means the for the zeroth order reaction, the rate is constant. However, in the rate doesn't depend on the initial concentration. For the first order reaction, T half doesn't depend on the initial concentration. So these things you have to obtain, you have to take care of. For the zeroth order reaction, again rate doesn't depend on the initial concentration, but T half, the half life of the reaction, it depends on the initial concentration. But for the first order reaction, what we see, T half, the half life of the reaction doesn't depend on the initial concentration, but rate depend on the initial concentration for the first order reaction. So for the first order reaction, if the initial concentration is increased, the rate will be increased in the similar proportion, the same order. So if it is one, suppose 1 molar, so the rate will be suppose 1 value from value, and if the initial concentration will increase 2 times, rate will also be increased 2 times. If initial concentration will increase to 3 times, the rate will also be 3 times of the initial value. So the rate depends on the initial concentration, but the initial concentration to the power only 1, power 1 only. So the rate, as to what many times you increase the initial concentration, to the similar times the rate will also be increased. However, for the first order reaction, what we see, the rate of reaction is proportional this value, k into initial concentration to the power 2. So the rate is equal to k into initial concentration of the power 2. So if the initial concentration was initially 1 and rate is 1, if you increase the initial concentration to, the rate should increase 2 to the power 2, means 4 times, and that is what we obtain. The second order reaction rate increases to the 4 times if you increase the initial concentration of the reactant, and if you increase the initial concentration 3 times, rate will increase 9 times. If you decrease the initial concentration to the 2 times, so the rate of the reaction will become 1/4 of the initial previous value. Now what we see, the T half is for the zeroth order reaction is equal to A naught divided by 2K. So T half here, as I said, you see T half of the zeroth order reaction depends on the initial concentration, but T half for the first order reaction doesn't depend on the initial concentration. Here there is no this expression, there is no term for the concentration, this expression, but the rate, this rate was depended on the initial concentration of the reactant. So rate, this expression value we see here, it will affect the rate as rate is equal to k into A for the first order reaction. However, for the zeroth order reaction, rate is equal to k, the value of k, so it is constant. For the second order reaction, this T half is equal to 1 divided by k into A naught. This A naught, you just this make this A naught as this A as A naught by 2 and this T as T half, and after solving this we will obtain T half is equal to 1 divided by K into A naught. You may not have to remember this expression. Even if you remember this expression, you can easily obtain this value. Now the units that we know, generally unit of K for the rate constant we know is equal to mole to the power 1 minus n liter to the power n minus 1 per second or per unit time. And this or the mole per liter is molar to the power 1 minus n at time inverse. This was the unit of rate constant, and the m is the expression is a molar per second if because the value of n is 0 for the zeroth order reaction. So 1 minus 0 is 1. So the molar divided by second. So molarity divided by unit of time is second. For the first order reaction, as is a molarity to the power 1 minus n, value of n is 1. So 1 minus 1 is 0. So the uh, unit of rate constant will not depend because m to the power 0 is 1. So it will not depend on the molarity, the unit of the molarity. So it is only 1 divided by second is the unit. For the second order reaction, as this is the molarity to the power 1 minus n, the value of n for the second order reaction is 2. So 1 minus 2 is a molarity to the power minus 1, and second to the power minus 1 is anyway there. So molarity to the power minus 1 into second to the power minus 1 is the unit for the second order reaction. Now you should remember that the order of a reaction is sometimes altered by the conditions, and altered by the conditions means what? If you remember, I have said earlier, if you increase the concentration of one of the reactant which was initially very important and it determines the rate of the reaction, but if you increase its concentration too high, to keep this concentration of this reactant too high, so a slight change in its concentration, decrease or increase, doesn't affect the rate of the reaction, and such reactions are called pseudo some order reaction. Whatever the left order is what, so that kind of things we obtain. So there are many reactions which obey first order rate law, although they are higher order reactions. So there are many higher order reactions there are which follow the first order kinetics or first order rate law. And the classical example for this is the hydrolysis of ethyl acetate. Ethyl acetate, if you hydrolyze it in the acidic or basic medium, and what do you obtain is the ethyl acetate. The hydrolysis in the acidic medium, here we see that for the hydrolysis we need to have the water molecules. So water molecules get consumed here, and so the formation of acetic acid plus ethanol happens. So acetic acid and ethanol are formed in this reaction, and if the concentration of water, if you take the concentration, because water is available freely and its cost is also very low, so one can take water in the excess. And once you take the water in excess, what happens in this example? Suppose that an initial value, I mean at the t is equal to 0, you have taken 0.01 mole of ethyl acetate and 10 moles of water you have taken. So water is already in excess, and the presence of acid, the initially what there was no acetic acid and no ethanol, because the reaction is just going to start. When at time t, suppose all of the ethyl acetate is consumed, so it is hydrolyzed to give, and once it is hydrolyzed, the 1 mole of ethyl acetate after consumption, it gives 1 mole according to stoichiometry, it will give 1 mole of acetic acid and 1 mole of ethanol. So 0.01 mole if it is consumed, it will give 0.01 mole of acetic acid and 0.01 mole of ethyl acetate. However, what we see, 9.99 mole of water will remain be there. So it means the concentration of water does not get altered much during the course of the reaction. It is just 10, from 10 it becomes 9.99 mole, which is almost equal to 10. The concentration of water doesn't get altered during this reaction. So the reaction behaves as a first order reaction. And now this reaction, that is why it behaves something as if it is a first order reaction, and such reactions are called pseudo first order reaction. Suppose a second order reaction is there, there are two reactions, and the rate of the reaction depends on the concentration of both the reactants as a part of order power of 1 in the rate expression. And if you take one of the reactant in excess, what you see, the reactant, the rate with respect to that reactant which was in excess becomes zero order. And so the overall order of the reaction which was second order means, suppose a this rate expression, if this water was not in excess, one should write rate is equal to k rate constant into concentration of ethyl acetate to the power 1 into concentration of water to the power 1. Once this concentration of water is very high, so rate will not depend on this, because it will depend on only the limiting reagent, because if the concentration for every ethyl acetate molecule, there are plenty of water. So water is now the water, this is not going to in the search of the water, and so for every ethanol molecule will surrounded by plenty of water molecules, so there is this effective collision is already be there. So the concentration of water does not get altered much during the course of the reaction. So the reaction behaves as first order reaction. Such reactions are called pseudo first order reaction, and this is the example. The example is the hydrolysis of ethyl acetate in presence of excess of water. The similar example can be the inversion of cane sugar, and the inversion of cane sugar, you see the cane sugar which contains the sugar sucrose molecule, and sucrose molecule is a dimer of the glucose and fructose that we know. If in the hydrolysis, what will you do? If you add water and in the acidic, slightly acidic condition, and this on the hydrolysis, this water molecule will be consumed and the glucose and fructose molecules will be formed. So this reaction, the rate k should be equal to the concentration of this to the power 1 and concentration of water to the power 1. As the water concentration is in excess, so even the concentration changing this, suppose here in this example itself the 10 mole of water we have taken, and instead of 10 mole of water, suppose we have taken 9 mole of water, even this reaction will go to the completion. Even if you take that instead of 10 mole 11 moles of water, the 11 moles of water also this reaction will go to the completion. So the rate of reaction, if the one of the reactant is in excess, it doesn't depend on the concentration of the reactant which is in excess. So here again the water is in excess, the water H2O to the power 1, which should ideally be, now if this concentration is very high, so it depends on that this concentration of 1 will almost behave as concentration to the power water to the power 0. So the rate will all, and concentration of water to the power 0 means the rate is what is equal to k into concentration of the cane sugar or the sucrose and to the power 1, and so this is the effective rate law, and this effective rate law is also this, again this reaction is also the pseudo first order reaction. Let's take this question. The first order reaction has a rate constant 1.15 into 10 to the power minus 3 per second. How long will 5 gram of this reactant take to reduce to 3 gram? So what we know for this reaction is this is the first order reaction. So order of the reaction n is equal to 1. The formula we have to use it for the first order reaction, and that is only information that we get from here. The rate constant value of rate constant k is 1.15 in 10 to the power minus 3 second, and the final concentration and the final value of the reactant, final amount of the reactant one can consider, though it is written as 3 in the terms of concentration, but this is the amount, and one can in the place of concentration one may also write it as the mass. So this 3 gram and this R naught, the initial value of the reactant, initial amount of the reactant is 5 gram. So, and this is the reactant, and this the same reactant, its mass, molar mass will be the same. So actually what we know that the number of moles, it should ideally be depend from the number of moles because it is a concentration. But since we know that this amount, the number of moles, this divided by molar mass of the reactant, this will also divided by molar mass of the reactant. Then the constant 3 gram is mass divided by molar mass gives the number of moles, and number of moles divided by volume is what the concentration. Since this reaction is happening in one pot, the volume is going to be constant, and the reactant is same, so the molar mass is also going to be constant. So what I am going to tell is, what I am telling actually is, instead of taking in concentration, one may also take directly the amount, direct amount in the gram, because this is not going to affect the overall result of this calculation. And why it doesn't affect the overall result? Because R, concentration of R, it is suppose concentration, how the we obtain the molar concentration. Molar concentration is the number of moles divided by volume, and the volume of this is not going to change usually, because the volume is the same for the reaction is happening, and same amount of the only the reactant is taking part, the solvent amount is almost same. So volume is same. So here, and the number of moles how will obtain of the number of moles of the reactant. So the mass amount of the reactant in gram divided by molar mass of the reactant. So 3 divided by suppose m. This is also 5 divided by m. And suppose the volume is V in this case. So 3 divided by m into V, and this R naught will be equal to 5 divided by m into V. And now the R naught divided by R, when we put here in the ratio, the m into V, this 5 gram divided by m into V whole divided by 3 gram divided by m into V. So m into V, m into V will be cancelled out. So what I mean to say, this expression can also be directly used as this, where X is the amount of the reactant. So this could be, one can write as X, I can write it as X, or the amount of the reactant, and this is the initial amount in gram. And this is because one can write this because R naught divided by R is equal to X naught divided by X. And that is why one can write it directly. So the T is equal to, now the T is equal to here. So T is equal to 2.303 divided by K log X naught by X, or that is R naught by R. Let me put this value here, and so 2.303 divided by the value of K is given 1.15 into 10 to the power minus 3 per second log this value X naught 5 gram divided by 3 gram. So 2.303, this 2.303 divided by 1.15 into 10 to the power minus 3 is equal to 2.003 into 10 to the power 3. This per second will become second, and this minus 3 becomes plus 3 when it goes into numerator, and 2.303 divided by 1.15 is 2.003. And this value is what? Log, this gram will be cancelled out. So this is log 5 minus log 3. And the value log 5, you can find out the value of log 5 from the log table, and log value of log 3. Both are of the base 10. So that value, the difference is 0.222. Now one can obtain this as 2.003 into 10 to the power 3 second into 0.222. And so this, on multiplying all this, what we obtain 0.444 into 10 to the power 3 second, and this is 4.44 into 10 to the power 2 second. This second unit is because of this. Now let's see the another question. The time required to decompose SO2Cl2 to half of its initial amount is 60 minutes. So half, that is T half, is given as 60 minutes. If the decomposition is a first order reaction, calculate the rate constant of the reaction. What is again given here? The reaction is the first order, so the N is 1. So the formula that we will follow is the for the first order reaction. And the T half for the first order reaction is given 60 minutes, and we have to obtain the rate constant of the reaction. And for that, we know the direct formula T half is equal to 0.693 divided by K. So the K is equal to zero point 0.693 divided by T half, and this is equal to 0.693 divided by T half is 60 minutes. So this is 1.155 into 10 to the power minus 2 per minute is the rate constant for this reaction. Now let's summarize few of the things that we have studied earlier. So rate of the reaction versus rate constant. These are two things. Sometimes a student gets confused between rate of the reaction and rate constant. Rate constant, that we know, it's a proportionality constant. So rate is equal to proportionality constant, rate constant into the concentration to the power order of the reaction. This is what we have obtained as the rate law. So this is from the rate law one can obtain the difference between rate of a reaction and a rate constant. So the rate of a reaction is a change in concentration of reactants or products in unit time. The rate constant is a proportionality constant related to the rate of a particular reaction. The rate constant, we know, it depends on the molar concentration of the reactants and products. The rate constant doesn't depend on the molar concentration of the reactants and products. We see later on, you will see the expression for the rate constant, and that expression for the rate constant we will obtain in terms of the Arrhenius equation. And we see the rate constant depends on the temperature and activation energy of the reaction, activation barrier of the reaction, or the activation energy one can also say. So the rate of the reaction, we have seen rate of reaction is defined in terms of the difference in the concentration divided by the time taken for that difference to occur. So, so the rate of the reaction now, it depends on the time taken for the reaction, because delta of the concentration divided by delta of the time, the delta t. So delta x one can say, or the delta r naught by delta t was the average rate of the reaction. The rate also depends on the time taken. The rate constant doesn't depend on the time taken for the reaction. We'll see how one can say these two things. Because for the first order kinetics, we see the rate constant is equal to 0.693 divided by T half. So how can one say that the rate constant of this reaction doesn't depend on the T half? That is the one thing that we obtain. But in the overall equation later on, that we will see the Arrhenius equation. Arrhenius equation is somewhere here. So you see here that this is the temperature, this is universal gas constant, and this is the rate constant. So in this equation, we don't see anywhere the expression for the t, the time. So the rate of the reaction, sorry, the rate of reaction, the unit for the rate of the reaction is concentration divided by time, because change in concentration divided by change in time. So change in concentration, the unit will be concentration, divided by time, the unit will be time. So the concentration, if it is represented in mole per liter, so it will be more per liter per second will be the unit of rate constant. However, what we see the uh, uh, unit of rate of the reaction, unit of the rate of reaction will be more per liter per second. However, for the rate constant, we have seen that the unit of rate constant depends on the order of the reaction. However, unit of rate of the reaction doesn't depend on the order of the reaction. It is always going to be concentration divided by time. If the concentration is in mole per liter, so the rate of the reaction for the any order reaction, the unit will be mole per liter per second. However, rate constant, the unit we see depends on the order of the reaction. If the order of reaction is n, so the unit will be mole to the power 1 minus n, liter to the power n minus 1 per second. Or if it is shown into the terms of concentration, it is, this is up to here is the concentration. So this is concentration to the power 1 minus 1 per unit time of divided by time. We have also studied about order and the molecularity. Let's see the difference between them. This is order and molecularity. What we know, the order is the sum of the powers to which reactant concentration are raised in the rate law equation. In the rate law equation, if you remember, the order is the sum of the powers of the powers of the reactant concentration. And the molecularity, as we saw it, as I explained earlier, if you remember, it is molecularity is defined for the, this is defined for the reaction that happens in the one step, or means the elementary reaction. So the number of molecules that take part in the rate determining step is only for this is only the molecularity is determined for the complex reaction. For a complex reaction, the molecularity is defined only for the rate determining step, or if the elementary reaction, it is the molecularity is defined for that step. So the number of molecules that take part in the rate determining step, the elementary reaction happens in only one step, and that step itself is the rate determining step. However, in the complex reactions which happen in many steps, the step which is the rate determining step means the step having highest barrier. The molecularity is the number of reactions that take part in that particular step defines the molecularity. So the order is applicable to elementary as well as complex reactions both. However, molecularity is applicable or defined only to elementary reactions. Order can be zero, fractional, or even negative with respect to one of the reactant. The overall order can't be negative though. So for any of the reactant, one of the reactant, one can see the order can be negative, fractional, or even means zero. However, molecularity cannot be zero or non-integer, because in the balanced equation we see we don't take any of the reactant, the coefficient are not fractional, non-zero. If in the elementary reaction any of the reactants are there, their coefficients cannot be zero or no, or fractional. So the molecularity cannot be zero or non-integer or the fractional. The order is experimentally determined and cannot be calculated. This point I have explained in much detail earlier. So this thing when you cannot, so whatever the concentration, whatever the power that is there in the concentration terms, that power, to what power, what the concentration terms should be raised, that power one can obtain only through the experiment. By doing experiment, one cannot predict that by any other method. The molecularity, for molecularity, what can do, the elementary reaction is there, you just balance the elementary reaction and then count the number of the molecules of each reactant, a total number of molecules of the reactant you just count, and you can theoretically obtain the molecularity of the reaction. So the molecularity can be theoretically obtained for the balanced elementary reaction. However, order cannot be obtained theoretically. One always needs to perform experiment to obtain the order. So for a complex reaction, order is given by slowest step, and molecularity of the slowest step is same as the order of the overall reaction. This is one thing one can understand by the common sense. The elementary reaction I have explained earlier, but I have not shown this graph, so let us try to understand this again. So a chemical reaction in which one or more chemical species, a chemical reaction in which one or more chemical species react directly to form product in a single step and with a single transition state and no intermediate is called the elementary reaction. So there are few more terms that are being introduced here, the transition state. So what we see here, this is the energy profile of the reaction, the energy of the all the species that are formed during the reaction and during when the reaction progresses. So what we see, when the reaction progresses, the reactant gets converted into the product. So once, if suppose this is for the exothermic reaction or exergonic reaction, the energy of the product is lower than the energy of the reactants. And what we see, the reactants first, their energy has to be raised to this level, then only the reactant will be converted into the product. This is a very basic theme or concept in the chemical kinetics, and this value, the difference from this point to this point, this energy value, this difference is called the activation energy. So reactant has to transit this transition state, it has to surpass this transition state structure or transition state value to get converted into the product. Sometimes the collisions happens, and the collision between reactants and that the energy of that collision, the what we see, it raises only up to the energy of the reactant only up to this point. But in that case, that collision will not lead to the product. Only few collisions, which are called effective collision, will lead reactant energy to the equal to the transition state energy or even more, and those transition only has potential to get converted into the product. Even if suppose a certain collision happens and the energy of the reactant reaches to this, from here there are two possibilities, may go to the reactant side and it may go to the product side. So in the transition state theory, this from reactant to the transition state is considered, it is assumed that the reactant is in the equilibrium with the transition state. And this conversion from here to here and the backward direction conversion is possible. However, from here to here, the only one, in this case, only one side conversion will happen to the product side. And when we see only one spike in that energy profile of a reaction, there is only one spike, then only one raise in this energy, there is only one transition state. Such reactions are called elementary reactions. So for this reaction, suppose this example, general example, we see there is only one spike, there is only one transition state. So this reaction is the elementary reaction. And the transition state, and we know this transition state is a state which exists for the very transient time, and that is what is called transition state. Although this is on the potential energy surface, this is a minimum from all other directions other than the line which connects reactant to the product. In this line, it is the maxima, otherwise on the potential energy surface, it is minimum from all other directions. So the non-elementary reactions or the complex reactions are what? The reaction in which the formation of product from original reactant take place through a series of steps are called non-elementary reaction. So a series of steps means at least two steps are involved in a non-elementary reaction, which are also called the complex reaction. So in this example, in this graph, as you see, the energy profile graph we call the energy versus the reaction progress graph, and the energy we see there is one transition step here for the first step, and there is another step involved in this reaction. So we see two spikes in this energy profile. So both spikes this represents one transition state. So there are two transition states in this reaction, and the two transition state means the reaction is happening in two steps. So after the first step, we see the formation of intermediate, and now this intermediate will collide or react to form product, and this will surpass. It will pass through the transition state 2, and this energy, and this will happen only if this energy is surmountable. If this energy is not surmountable, so what do? We try to increase the temperature, we try to heat the reactant so that the energy of the collision will be increased, and because of that, this energy, if this is very high energy, activation energy very high, it may surpass that barrier. So this kind of things, the activation energy is also called the barrier of the reaction. So out of the different barriers, suppose this barrier is, as we can see here, is smaller than this barrier. So the second step, this one, since this barrier is larger, so this step for this reaction is called the rate determining step, because this barrier is higher, and so this barrier is higher. So this step will be the slowest, slower than the first step. So this step is the rate determining step. The overall reaction is the complex reaction. This is elementary reaction number 1, and this is elementary reaction number 2. So there are two elementary reactions that are involved in this complex reaction. So the elementary reaction are single step reaction, whereas non-elementary reactions are multi-step reaction. Elementary reactions are simple in nature, while non-elementary reactions are complex. And complex means they happen in more than one step. And now these points, we can see the dependence of, we have seen the dependence of rate on the concentration, and the concentration and that this thing we have seen in details for the first order, zeroth order, and in slight details for the second order reaction as well. Now what we know, the rate of a reaction also depends on the temperature. The rate increases with increasing temperature, since the kinetic energy of the molecules increases with temperature, leading to more collisions between the gaseous molecules. The more collisions, number of collisions will increase, and the number of effective collision will also increase. with the increase in temperature. Then the presence of catalyst, this is another factor that affects the rate of the reaction, and the surface area of the reactant, or even if the catalyst, it is the heterogeneous catalyst, it also affects the rate of the reaction. These things we will see in the next class, the following class. Let me stop here.